In one of our previous lessons, we learned about how to find and identify relative extrema by analyzing intervals and using the first derivative. Now, the title for today's lesson, Absolute and Global Extrema, is a little bit off because I'm actually going to be talking about extending that knowledge in two ways. First, we're going to be talking about actually a new and faster way to classify stationary points. It's not always going to work, but when it does, it's really, really quick. And second, I do want to extend our knowledge of relative extrema into the concept of global and absolute extrema. So those are going to be the two things that we're going to get into in this video. But before we do that, let's go ahead and take a deep breath. And let's begin. So the method of classifying relative extrema that we're going to learn or relearn or review today really goes about using concavity. And I want to point out what we learned over the last few lessons about analyzing intervals is not wrong, it's not bad, it's still totally valid. In fact, the great part about that method is that this method always works. So the interval analysis method will literally always work for classifying relative extrema, for helping you to know whether it's a maximum or a minimum. The trouble with the method is that it's time consuming. You have to find all of the stationary points, then you have to set up intervals, then you have to test all of those intervals, and at the end of all of that, yeah, you're guaranteed to have something that worked, but it took a lot of time. The next key point that we have, this thing that I'm going to talk about next, is going to give us a quick but not perfectly reliable way to classify extrema using the concavity of our function as a guide. So what that means is that this method, when it works, is faster, but when it doesn't work, you're going to need to go back to using the interval method that we had from before. So with that said, let's get into this idea, right? So for this key point, let's assume that we have a function f of x and it has a stationary point at a. Those definitions are really just going to sort of help to ground us so that we're all talking about the same thing. So here's what this says, right? If the second derivative at that stationary value, at that critical number, if that second derivative is positive, then the function has to have a minimum there. And the reason is that the function is concave up there. If you have a concave up function that has a stationary point in there, that stationary point has to be a minimum. Okay? Similarly, if you go through and have a stationary point and you plug that stationary point's x value into the second derivative and you get a second derivative that's negative, then the function must have a relative maximum there. And again, the reason is because the second derivative being negative means that the function's concave down. And if you think about what concave down looks like, concave down with a stationary point has to look like this. And that means that there's a maximum there, right? So effectively, what we can do instead of setting up the intervals up here is as soon as you get those stationary x values, plug them into the second derivative. If the second derivative is positive, you're looking at a minimum. If the second derivative is negative, you're looking at a maximum. Here's the trouble. The trouble, and I'll use red for this, the trouble is if your second derivative is 0, then we can't tell if it's a maximum or a minimum using this method. That doesn't mean it's not one or the other. That doesn't mean it's a saddle point. It means we literally don't know. It means that this method has failed us, and in order to classify it, you're going to have to go back to analyzing intervals. Okay? So again, the idea is you can use the second derivative to test and find out if a stationary point is a maximum or a minimum, but if you get 0 out of the second derivative, it means we don't know, and we have to analyze intervals to figure it out. With that said, we're going to go ahead and practice this a couple of times, and then we'll move into the rest of the lesson. Okay, so here's this first straightforward example. We're being asked to find and classify the stationary points of this function. Okay? So the first thing we need to do is we need to find the stationary points. Right? So to find them, we need to look at where the first derivative is 0 or undefined. So I'm going to take this derivative. The derivative of this function is going to give me 10x to the fourth minus 20x cubed, and the plus 3 is just going to vanish. Okay, great. So I've got that. This can't be undefined. Can't be undefined because there's no division by 0, there's no asymptotes, anything like that happening. So I just need to set it equal to 0. At the same time, I'm going to go ahead and factor this because this is almost always my method for this. So I can factor out a 10x cubed. Doing that leaves me with x minus 2. And so what I find is that my stationary points are going to be at x equals 0 and at x equals 2. Okay? So what we would normally do at this point is we would set up our intervals and then we would test those intervals. But we're going to try this new method, right? Our new method says that what we can do is we can evaluate the second derivative of each of these values to find out what happens. So let's sidestep for just a moment, or maybe we should sort of make our work clear. Let's write a quick statement that will try to classify these stationary points by investigating the concavity. It's a good habit to get into the idea of sort of notating your work. This is something that you want to do for your IB exam. It's great to practice in your homework, but it's also a really, really good thing to do in those mathematical explorations and in your mathematical writing. So in order to investigate the concavity, I'm going to need the second derivative. So my second derivative, f double prime of x, is, well, here's the first derivative. The derivative of this is just going to be 40x cubed minus 60x squared. Okay, great. So now what I need to do is I need to look at what is f double prime of 0 and what is f double prime of 2. Well, f double prime of 0, bummer. When I plug 0 into this thing, I'm going to get back 0, which means that concavity didn't tell me anything. So I'm going to have to refer back to the intervals anyway. But maybe f double prime of 2 will still be helpful. Let's find out. F double prime of 2 is going to be 40 times 8 minus 60 times 4. So when I actually do this, f double prime of 2 is 320 minus 240. So we can see really clearly there that f double prime of 2 is greater than 0. So because of that, because the second derivative is positive, it means that my function is concave up there. So what does that tell me about that stationary point? Doesn't that tell me that that one is a minimum? So again, remember, it's not just enough to, do a little computation here and then say, therefore minimum. You want to make sure that you're actually writing out some reasoning here. Now remember, our question also asks us to find the stationary points, not just the locations. So I actually need to find the value. So what I'll be doing here is I'll be taking the 2, the location of this stationary point that I know about, and I'm going to plug it back into the original function to figure out what the y coordinate for that thing is. So down here, if I do f of 2, I'm going to get 2 times 2 to the 5th minus 5 times 2 to the 4th plus 3. And so if I keep working through that, let's see here. We're going to have f of 2 will be 2 times 32, that's 64. 64 minus, this is 16 times 5, that's 80, plus 3. This is going to be negative 16 plus 3, so that's negative 13. So that means that we have a minimum at 2 comma negative 13. Okay? All right, so we figured out what happened at 2, but this quick method sort of failed us over here at 0. So we know that when that happens, we're going to need to go back and use the other method. And that seems frustrating, but the good news is some of our work is actually already done. Instead of needing to set up 3 intervals, I only need to set up 2. I need to look to the left of 0, so that would be from infinity to 0, and then to the right of 0, and that would just be from 0 to 2. So remember, we would normally have to have had a third interval over here that was from 2 to infinity, but I don't need that. I don't need that because I know what happened at 2. I just need to know what happened at 0. So in order to classify the stationary point that I have here, I'm going to need to know what the first derivative was. So I'm going to go back up here just a bit so we can see this derivative. Remember, I like to use the factored version of it to do this, because all I really need to do here is I need to pick a representative, right? I just need to do f prime of negative 1. So if I plug negative 1 into this thing, I'm going to get 10 times negative 1 cubed times negative 3. I can see pretty clearly that this is going to be positive 30, right? So we can see over here that my derivative is positive. That means my function is increasing, right? So f of x is increasing. Okay? And then over here between 0 and 2, I need to pick a representative here. I'm going to do f prime of 1, right? And so when I plug 1 in up here, I'm going to get 10 times 1 cubed times negative 1. That's f prime of 1 being, let's see here. So this time this is negative 10, and that means that here f of x is decreasing. Okay? And so now that I know that, now that I can see that my function is changing from increasing to decreasing, what can we tell is happening at 0? Right? Therefore, at x equals 0, f of x has a maximum. Okay? And so the last thing I need to do is I just need to take that 0 value and plug it back into my original function just like I did over here. So f of 0 is going to be 0 minus 0 plus 3, which means it's 3. And so we have this maximum at the point 0, 3. Okay? Maximum at that value. So this example sort of gave us a picture of what it looks like when you've got our quicker method worked for one of them, but then it failed for the other one. We sort of had to do the long method here. If this is all making a lot of sense to you, I want to throw one more like mini shortcut at you, just as a thought, right? I would hold we didn't maybe need to do, and it wasn't a lot of work, but another way we could have known this was decreasing, because this thing had a minimum of 2, doesn't that mean it had to have been decreasing on this interval and then increasing on this one? So it's kind of like, because my quicker test worked here at 2, I kind of knew the function had to be decreasing here. If that makes sense to you and you feel like you can write the rationale for that on this interval, you can do that. Just make sure that you're putting sufficient reasoning and that you're writing all of that down. We are going to do one more example of using this sort of different method for classifying extrema, and then we'll move on to the second part of the lesson. Okay, so here again, I'd like us to find and classify the stationary points of the function 4x minus e to the 2x. So go ahead and pause the video and use the method we did in the previous one. Find the stationary points and then plug the x values into the second derivative and use that concavity to try and determine whether those stationary points you found are the locations of maxes or mins. So the first thing I need to do here is I need to find the stationary points. So f prime of x is going to be, well, the derivative of 4x is 4, and the derivative of e to the 2x, that's a chain rule, so minus 2e to the 2x. Okay. Again, this is not undefined anywhere, so I don't need to worry about that, but I do need to look at where the derivative is 0. Okay, so attempting to solve this, I'm going to move this over, and then we can divide the 2. E to the 2x equals 2, and then I can do a natural log. So 2x equals the natural log of 2. That means that the only stationary point that I have here is 1/2 natural log 2, which I could actually write as natural log of the square root of 2 if I wanted. Either one of these things is going to work fine. So this is sort of my x coordinate. What I'd like to do next is I'd like to try and classify this. I'd like to try and determine whether this thing is going to be a maximum point or a minimum point. But maybe while I'm here, maybe I should plug it back in to find out what its y coordinate is. Like while I can see f of x here, let's do that real quick. So if I wanted to do f of 1/2 natural log 2 and plug this thing in here, I'd have 4/2 natural log 2 minus e to the 2 times 1/2. So that's just 1 natural log 2. So this means I've got 2 natural log of 2 minus e to the natural log 2. That's just going to be 2, right? So, yay, that's my y coordinate. It looks like this point is the natural log of the square root of 2, comma, and then this y coordinate. I want to put this thing up as a power. I think it's going to look nicer as natural log 4 minus 2. So that's the point. This is my stationary point. Now I just want to know if this is a max or a min or neither. So I'm going to try and use my quick method for this. For my quick method, and we should write about that, right? We should take a moment to write down, what are we going to write down to indicate to our grader or to our reader that we are going to test this using concavity? So hopefully you wrote down or said or were thinking something like, we're going to attempt to classify the stationary point by considering the concavity of the function. Right? So to do that, I need to do a second derivative. My second derivative is, well, the 4 is just going to vanish. And then I have to do a chain rule again on this. So it looks like it's just going to be negative 4 e to the 2x. Okay. Now, you've sort of got two options here. One of them is that you can plug this in and show that it's negative. Your other option is to look at this and if you can say confidently that this function is always negative, you can sort of say, hey, this function is always concave down, which means what do we know about this stationary point? Since the whole thing's concave down, this has to be a maximum. But I think a lot of you might be uncomfortable with that. So remember what we do here is all I need to do is test this at our value, at the natural log. Now, maybe I want to use that one, at 1/2 natural log 2. So this would be negative 4e to the 2 times 1/2 natural log 2. Giving myself a little more room here. The second derivative is negative 4e to the natural log 2. E to the natural log 2 is just 2, which means this is negative 8. So the last thing we need to do is we need to write something down, like because this second derivative is negative, the function is concave down, which means this is a minimum. Okay, I made a little error there. It's not a minimum, it's actually a maximum. I decided to leave that error in, though, because it's really easy to make that mistake. We see this negative thing. This negative thing means it's concave down, and we start feeling and wanting to say minimum. But remember, if my function is concave down, the thing that I found has to be a maximum, right? So we have a maximum at natural log of the square root of 2, comma, natural log 4 minus 2. So hope you don't mind that I left that error in. I just wanted you guys to see how easy it is to say that. Remember, we do also want to write our reasoning here. So part 2 of this lesson is effectively about the idea of a global or an absolute maximum or minimum. And so the idea here is that we've already learned about relative maxima and minima. Relative maxima and minima are the lowest and the highest values nearby, or like in a neighborhood of a point. But the absolute highest or lowest value that a function takes are called the global or the absolute maximum or minimum. By the way, this idea of an absolute maximum or an absolute minimum can either be on the entire domain or it can be on just an interval. I want to look at a couple of graphs of this just so we can sort of see what it looks like before we dig into like how we find these things analytically. Okay, so in this first graphical example, I've given you a function here, I've given you a graph, and I'm now asking in this first question to find the absolute maximum and minimum of this function, right? Since I don't give any domain in this, we're asking about the absolute or the global maximum or minimum of the entire function on the entire domain, right? So as far as a maximum is concerned, what's the highest value this function takes on? Right? And you might be inclined to say infinity. It's not actually a value, though, and so we would just say here that this has no absolute maximum. Now, the second part of this question asks about the absolute minimum, right? Well, for this particular function, we can see that the minimum value is, right down here, right? And I know this isn't entirely precise, but if we sort of look sideways, this looks to be about negative 18. And it looks like it probably happened at around negative 2.5. Now, I want to sort of address something really important here. This question is asking about the absolute minimum of the function. So sort of precisely here, the answer that we would give here is that the absolute minimum of this function is negative 18. So it's not necessarily the point that they're asking for. If they said the minimum point, then you could give it as a point. I think the way I personally prefer to answer this question is to say that it has an absolute minimum of negative 18 at x equals negative 2.5. And again, I'm sort of estimating those values because we're not doing this analytically. We're sort of looking at it just graphically to have a sense of what's going on. Okay. Now, what about finding the absolute maximum or minimum on an interval, right? So what if I'm now sort of restricting myself and only looking at this between negative 4 and positive 2, right? On that interval, can we tell what the absolute maximum of the function is? Does this function have an absolute maximum on that interval? And the answer is yeah, because if I'm only looking at this between negative 4 and positive 2, then the absolute highest it gets seems to be right about there. And that seems like, maybe that's 1. So this function has an absolute maximum of 1, and that happens at x equals, I don't know, maybe that's it. Maybe it's at about half. So again, I want to point out, when they're asking about the maximum or the minimum, they're specifically referring to the y value, the output value of the function. It is nice also to tell them where that happens, but I like to shy away from just saying 1/2 comma 1 is the absolute maximum. I like to focus on the fact that the maximum refers to the value of the function. Now, what about the minimum? Well, the absolute minimum of the entire function happened to be on that interval, so this same absolute minimum that we got also applies. So this has an absolute minimum of about -18, which happens at x equals -2.5. So I hope that sort of makes sense here. We're going to go through one more graphical example, so there will be one for you to kind of do on your own, and then we'll work on finishing out the lesson. All right, so here I'm effectively asking the same questions, finding the absolute maximum minimum, but the function is different this time. This looks like it's sort of like a kind of a slanted sine function kind of thing. So first question, what would the absolute maximum and minimum value of this function be across the entire domain? Pause the video, think about that for a moment. Or maybe you already know. This thing doesn't have an absolute maximum or an absolute minimum. It really looks like this function is going to continue to sort of move in an upward trend, and this is going to continue to move in a downward trend this way. It's not going to reach a highest point or a lowest point. So we would say that this function has no absolute maximum or minimum. But just because it doesn't have an absolute maximum or minimum on its entire domain doesn't mean that it might not have one on a restricted domain. So if I now ask the same question, but on the restricted domain from -4 to 2, so if I was only looking at this thing between -4 and +2, right, we might be able to see here that, yeah, this function does look like it has an absolute maximum, right? So pause the video and think for a moment, what is the absolute maximum and what is the absolute minimum when we restrict ourselves to this smaller domain? Well, it looks like the maximum value happens right up here. That looks like it's, somewhere close to 5. Might be 4.5. I'm going to go ahead and just put 5. An absolute maximum of about 5, and it looks like this happens it actually looks like it happens almost right at the end of this thing here. This looks like it might even be at x equals 2. As far as the absolute minimum is concerned, the lowest value we ever get down to is this one down here, which looks like it, again, might be -5, might be -4.5. I'm going to just go with -5. We're just approximating here. So an absolute minimum goes all the way down to a -5, and it looks like that happens at x equals -2. Okay. So I hope that made sense. I hope that you're sort of getting and seeing what this idea of an absolute maximum and minimum are versus a relative minimum or maximum. The last thing that I want to say related to absolute maxima and minima is that there's a sort of a neat theorem or key point that if you have a continuous function, now a continuous function means a function with no holes or asymptotes or jumps, so a continuous function on a closed interval, that continuous function on the closed interval will always have an absolute maximum and an absolute minimum. Moreover, those absolute maximum minimum values will always be found in one of two places. They're either going to be at stationary points or at the endpoints of the interval. So to reiterate, if you have a continuous function on a closed interval, you will always be able to find a highest point and a lowest point, and the only places that you'll find them are at stationary points or endpoints of the interval. So if you're ever in a problem where it's asking you to find the absolute maxima and minima, what our procedure is you first find all of the relative maxima and minima from the stationary points. Then you find the value of the function at the endpoints of the interval. And then step 3 is actually kind of silly. You literally just circle the biggest one and you circle the smallest one. Because those are the only places they can happen. So to find absolute maxima and minima, you find all the potential ones and then pick the ones that are the absolute biggest and the absolute smallest, and you're done. So we're going to do one example of that, and then we'll be done for the day. All right, so here we go. Let's try this out. We're being asked to find the absolute maximum and minimum of this function on this interval. So the first thing that I would say is this function continuous? Does it have any holes or asymptotes or jumps or things like that? And really the way that we check for this is, does this thing have anything that's going to cause division by 0? Or do these functions have any built-in asymptotes? Absolutely not. The x function is just a straight line. Cosine is a nice, smooth, continuous trigonometric function. So we're fine here. This is a continuous function, and the interval that we have is a closed interval. So because of that, we are guaranteed to have an absolute maximum and a minimum. So now all I need to do is find all the potential ones and see which ones are the biggest and the smallest. So let's take the derivative of this and set it equal to 0. Let's find the stationary points. F prime of x is going to be 1, and then the derivative of negative 2 cosine x, that's going to be plus 2 sine x. And then finding stationary points, I set this equal to 0. 0 is 1 plus 2 sine x, and then if I go about solving this, I'll have 2 sine x is negative 1. That means sine x is negative a half. Then if I think about my unit circle, sine is negative a half when x is, let's see here, if I'm thinking about a unit circle, sine being negative a half would be here and here. That looks like it's 7 pi over 6 and 11 pi over 6. Now, it's kind of like good news here. We don't actually have to test whether these things are maxima or minima. I'm just trying to find the absolute max and min. So all I need to do here is evaluate what is f of 7 pi over 6, and what is f of 11 pi over 6, and then what's f of 0, and what's f of 2 pi. And after I get these 4 answers, I just pick the biggest one to be the absolute maximum and the smallest one to be the absolute minimum. So if we take these things and evaluate them in this function up here, this will be 7 pi over 6 minus 2 times, let's see here, the cosine of 7 pi over 6, that's going to be negative root 3 over 2. So the 2's will cancel out. This will become positive. Looks like I've got 7 pi over 6 plus root 3. For the next one, I'll have 11 pi over 6 minus 2 times, and in this case the cosine is the positive square root of 3 over 2. So the 2's will drop out, and this is going to be 11 pi over 6 minus root 3. All right, and then it's f of 0, so I'm taking 0 and plugging it up here. This will be 0 minus 2 times the cosine of 0, which is 1. That's negative 2. And then finally plugging 2 pi in up here, I'll get 2 pi minus 2 times, and again the cosine of 2 pi is also 1, so this is 2 pi minus 2. This one right here is clearly the absolute minimum, right? Because it's the only one of them that's going to be negative. With these other ones, we may need to actually compute them. So using the calculator, this first one is 5.40. This one here is 4.03. And this last one is 4.28. And so my absolute maximum was this one over here. Right? So I have an absolute maximum of 5.40. So when you're asked to find the absolute maximum and minimum on a closed interval, this is the process that we use. We look at the relative max and mins, the stationary points, and we look at the endpoints of the interval, and we choose the biggest one to be the max and the smallest one to be the min. Hope that all made sense. If you have questions, as always, please let me know, and I wish you best of luck as you work through this practice.